Want me to go ahead?
Yep, I'm ready to go.
Thank you, Tom.
Okay.
All right. Hello, everyone, and thanks for joining us today in the last episode of this data science development series. As I posted on LinkedIn, actually, it surprised me. It was really interesting to see that we approached the end of this series, which we started with Machine Learning 101, and then Computer Vision 101, Deep Learning 101, NLP 101, Search Relevancy 101, and now Recommendations 101. So it has been a very interesting journey, I would say. We learned a lot, even it's a 101 series, but even for the senior data science people, it was interesting and refreshing to actually kind of refresh our minds about the basic skills and the things that we use every day in practice. So today I'm gonna cover Recommendations 101. Recommendation is one of the very interesting areas of data science. And as we're gonna see during the talk, it's actually one of the best, let's say, data science practice that improved return of investment in companies. And with that, let me start. So about myself, my name is Khalifeh Jadda. I'm Director of Online Core Data Science at Home Depot. My organization include Core Search Data Science team, Core Recommendations Data Science team, and Visual AI team. Aside from my full-time job at Home Depot, I'm also the founder and chair of the Southern Data Science Conference, which takes place every year in Atlanta. And in 2018, actually, we hosted as well in Orlando. So this year, due to the pandemic, as we all know, the conference was postponed from April to mid-August. As of today, the conference will take place August 12th to 14th in person at Cobb Galleria, and we're gonna offer a virtual option for people who don't feel comfortable to show up in person. So that's the plan for now. We got the confirmation from the venue. By the way, it's a government venue. So they implement all the CDC precautions and regulations carefully. So we got the confirmation that's gonna happen in person mid-August. Phantom Insights is a new startup that we founded. I co-founded with some colleagues and friends from the Middle East and North Africa region. So the focus of this startup is providing data science and AI solutions in the Middle East and North Africa region. And lastly, I'm also a co-founder of Athletics, Atlanta Analytics for Community Service, which is a nonprofit organization that serves Atlanta area with the talent and the power of, like, we try to leverage the power of data science and analytics for community service. Some of the projects we did, including fighting human trafficking with data, including fighting homelessness with data, and so on. My education background, I have Ph.D. in computer science from University of Georgia. And I'm actually serving as on the board of directors of the Institute of Data Science and Analytics at Kennesaw State University. And I served before as senior research scientist at the Legal Analytics Lab, Georgia State University. So as you can see, very well rooted in Georgia. All right, so let's start the fun. Recommender systems. I think overall, every day, somehow we engage with one of the information retrieval systems. And information retrieval systems include search engines and recommendation engines. So last week, Trey Granger covered the search relevancy, right? And he covered the search engine and how searches happen and how we improve relevancy and all that kind of things, which is, again, this is one system of information retrieval systems. The second one is recommender systems. And the way to look at recommender systems from high level is it utilizes knowledge discovery and AI techniques in order to predict items of interest to individual users and subsequently suggest these items to them. So ultimately, recommender systems try to predict the interest of the customers and leverage that to basically show them items that match their interest. So very popular recommender systems that, as I said, like almost every day we deal with. If you are a big fan of movies and TV shows, and you have subscription with Netflix, it is important to know that 80%, that's based on Netflix reporting, 80% of Netflix showing or watching happen actually as a result of recommendation. So you can think of 80% of the stuff that you watch on Netflix actually is driven by recommendation. Also, on the other hand, in the e-commerce, Amazon report that 35% of their revenue is actually driven by recommendation. So if you think of Amazon revenue, which is about $280 billion, 35% of that is nearly $100 billion. And that $100 billion, to just put it at a scale, it's almost, it matched Microsoft's revenue in 2 years ago. And it is almost the revenue of Uber. So that's a lot of money that is driven by recommendation. That's I said at the beginning, recommendation or recommender systems, they actually prove return of investment, huge return of investment in companies. That's why it's like an area of investment in each e-commerce company and video streaming and things like that. So the agenda of this talk, just to give you a heads up. So we're gonna go over now this brief introduction. Then we're gonna go through the most popular techniques to build recommender systems. That's the fun part of the talk, which is the technical aspects. We're gonna cover collaborative filtering. Then we're gonna cover actually the problems of collaborative filtering and how we overcome those problems with matrix factorization, the factorization machines, and then we're gonna move towards the content-based recommendation. What is the difference between that and collaborative filtering? What are the problems that we solve with content-based, the techniques we use to build content-based recommendations? And then after that, we're gonna talk about the breakthrough that happened in recommendation systems, which is like using deep learning for recommendations. We're gonna cover the deep factorization machine, the extreme deep factorization machine. We're gonna cover the wide and deep model. So we're gonna cover also a wide range of deep learning models. And at the end, I'm gonna cover actually an actual use case of how we built a recommendation algorithm at scale for Home Depot using one of those deep learning techniques, which is the bidirectional LSTM. So with that, if you look at around you now in the digital world, you will see recommendations everywhere. It's not just e-commerce, it's not just Netflix, it's not just Amazon. So recommender systems are in e-commerce. As we said, at Home Depot, when you go shop, you will see that if you are buying a grill or interested in a grill, that we're gonna show you, hey, with a grill, maybe you should take also grill cover and barbecue kit, right? So this is an example of recommendations. In e-learning, when you go to Coursera, there is a list of recommendations for courses that you can take according to your interest, according to the things that you expressed interest in the past. And then social network, for example, on LinkedIn, you will see usually people you may know. This is another kind of recommendations in the social network. And in the recruitment domain, when you go to websites like Indeed or Career Builder, you see, again, list of recommended jobs for you, for the job seekers. You receive emails with recommended jobs for you. At the video streaming, as we said, like Netflix, 80% of the watches on Netflix are driven by recommendations. Real estate, if you go to Zillow or Trulia, you're also gonna see lots of recommendations. They recommend properties according to the price range you're looking for, according to the region that you're looking for, geographic area, and so on and so forth. All right, so let's talk about the first popular technique in recommendations, collaborative filtering. This is actually one of the most popular and tend to be actually one of the most successful techniques in recommendations, because collaborative filtering, if you think about the basics of it, is you are using the intelligence of a human to actually decide what is relevant and what is not, what goes with each other and what is not. So the idea of collaborative filtering is you want to leverage what the other users have done and expressed interest to actually influence similar users. So let's take now this example. We have Amy and Amber, and they both watched Avatar, right? Amy actually continued and she watched also Matrix. So she rated Avatar with 5 stars, she liked it. Then she watched Matrix and she rated with 5 stars. On the other hand here, Amber, she only watched Avatar and she rated with 4 stars. So that means she liked it. And now we would like to show Amber some recommendation. We want to recommend a movie for Amber to watch. So in this case, if you think of this scenario, if it turns out that I can tell that, okay, they both watched Avatar, they both liked Avatar, then it is safe to say that if I recommend matrix to Amber here, that's going to be of her interest. So this is basically the very basic logic behind collaborative filtering. So we learn from similar users, and we try to take whatever they have done, which the other users have not done yet, and we try to recommend those items to them. So moving forward, let's now look at the different kinds of collaborative filtering. So we have user-based and we have item-based collaborative filtering. And let's look at the difference between those two, because this is something you usually gonna hear. Is it user-based? Is it item-based collaborative filtering? So let's take this example. As we said, we have a list of users in the rows, and we have a list of movies in the columns. Now each user watched a movie, rated that movie. So Amy rated Avatar, Matrix. She didn't watch Titanic. So this is actually not rated. She watched Big Six, she watched Transformer, and the other users did the same. From recommendation perspective, what you see here, what is interesting to us really is not actually those ratings. What is interesting are those empty cells in the table. Those empty cells actually are the potential or the candidate pool of items or movies that I can recommend to each of those users. So for Amy, I have only Titanic left that she didn't watch. Assume that this is only my pool of movies or my inventory. But for Amber, I have Matrix and Big Six. So which one should I pick, Matrix or Big Six for her to show as recommendation, right? So let's take Amber now as an example. What is the difference between user-based collaborative filtering and item-based collaborative filtering? User-based collaborative filtering says you need now to find similar users, which means rows, to Amber who rated Matrix and Big Six. So basically what you try to do in user-based collaborative filtering is you try to see other users, in this case rows. I'm trying to find similar rows, similar users, who actually already watched and rated Matrix and Big Six. And then I try to find the most similar user to Amber, and based on those users' ratings of Matrix and Big Six, and I can take the average ratings, whatever, and then I can decide which one to show her. So this is what we call user-based collaborative filtering. On the other hand, if I'm implementing item-based collaborative filtering, in this case, what I need to do is I need to find items, columns, similar to Matrix and Big Six. So the two movies that I'm trying to estimate the ratings for Amber, I need now, instead of looking at the rows, I need to look at the columns. And then I need to find similar, items that has ratings. And then according to those similar columns, I'm gonna predict the ratings of Matrix and Big Six and decide which one to show to Amber. Now, if you ask the question, okay, which one should I pick, user-based or item-based? Based on the practice in industry, it actually shows that, or it turned out that item-based collaborative filtering seems to be more accurate than user-based collaborative filtering. But there is no theory behind it, like there is no mathematical proof behind it. It's just in practice, it tends to be that item-based collaborative filtering is more accurate than user-based collaborative filtering. All right. So we mentioned here a few times, okay, you need to find similar users. You need to find similar items in item-based collaborative filtering. So how can you measure similarity? That's the big question now. So let's take this again, extend our example, and let's look at the ratings by Amy. And in this case, we're gonna call these ratings Rx. So X refers to Amy, and RY are the ratings by Amber, which is our user Y. So if I have the ratings of X, Amy, and Y, Amber, we have three ways to measure similarity. I just pick actually those three due to their popularity. Jacquard similarity, cosine similarity, percent correlation. So if I look at Jacquard similarity basically look at the intersection over the union of the two users or the two sets that I'm trying to measure similarity between them. So at the end, the ratings by Amy and the ratings by Amber, I look to them as sets, and I'm trying to look at the intersection and then the union, and that fraction is actually the similarity between those two. What is the problem here? The problem here is I'm not taking the values of those ratings. So regardless if the rating was higher, like, or lower. If Amy said 5, Amber said 1, as long as they rated the same movie, the intersection gonna count that as 1. And then that means basically that they're gonna seem as similar. However, they gave different ratings. So the value of the rating is not taken into consideration when we take Jacquard similarity. That's why it's not actually helpful. The cosine similarity, on the other hand, treats the ratings in this case as data points, as points in a space. And when you take them as points in a space, then the way we measure the similarity in this case, I put here just for to clarify, you can see at the top of this slide, like this item C, query item A, item B. So you can think of now you have vectors in Jacquard space, or in Euclidean space. And what you want to do is you want to measure actually the cosine, the angle between those vectors. And this is actually the idea behind the name. So cosine similarity, we treat those ratings now as points in a space instead of as sets. And we actually measure similarity by looking into those vectors in the space, the angle between them. The last one, person correlation. In this case, we actually try to look at the correlation, the impact of, or the influence by each ratings on the other one, by each user on the other one. And the new actually item or a new variable that I introduced here, which is SXY, is actually the shared rating between X and Y. So we look at the shared ratings between those two, and then we take the average rating of X, the average rating of Y, and we try to estimate the correlation between user X and user Y. So those are kind of the similarity metrics that you can use to estimate similarity. When we said in the collaborative filtering, you need to measure to find similar users or similar items. So this is usually the way how you do the similar users and similar items. All right, moving forward. So this, as of this point, collaborative filtering seems straightforward, right? So you have kind of fill in the blank, where I have users, I have items, in this case movies. I just need to find similar users who rated the blank or empty cells here, and then take their ratings, and their ratings, since they are similar users, their ratings actually should reflect what Amber is interested in. And then I can recommend those items. What is the problem? The problem here is, if you think of, right now we're talking about few rows and few columns. Let's think about the scale of Netflix or the scale of YouTube. Millions of items and hundreds of millions of users, right? If you think of the matrix size, you can't even imagine. It's huge. And if you think of how, like, think of yourself, how many videos you would watch out of the hundreds of millions or millions of videos that each platform has. So you can think of a huge matrix with tons, lots of empty slots, zeros, unranked, and a few slots with values, which is basically the things that the user actually watched. So this sparsity, this is what we refer to as a sparsity problem in recommendation. So the recommendation, if you want to take the rating matrix, it is sparse. It is very sparse. And this introduced lots of problems, scalability problems, including the computation, and also that's going to impact, like, any traditional machine learning model that you want to train on a sparse matrix like that, most likely going to fail, because those zeros, they're going to introduce lots of noise, because it's basically, they are not helping the algorithm to learn anything. So with that in mind, that the sparsity curse is there in this scenario for collaborative filtering, what are the solutions? The first solution we're going to discuss now is the matrix factorization. But before I go to matrix factorization, I would like to see if Tommy has received any questions, so we can answer them before we switch to the matrix factorization. Do we have any questions, Tommy?
No questions yet. I think you're pretty much covering everything in detail, so no questions yet.
Thank you. Okay, so moving to matrix factorization. Matrix factorization came actually to solve the sparsity problem that we talked about in collaborative filtering. So collaborative filtering, to give a credit to the technique itself, is really one of the best performing recommendation techniques, because again, it used the human intelligence. We are using the people judgment to basically know what is relevant, what is not. But again, when it comes to the scalability and the computation issues, it has lots of those issues. So in order to put it in place in production at a scale, at the web scale, the first thing, or the first popular solution, was the matrix factorization. So matrix factorization, the idea here is you want to take this sparse matrix, which is basically represent the rating matrix, users and items with the ratings here. And as we said, imagine that this matrix is million by million, 100 million by 100 million. This is the M and N in this case. What we want to do is we want to split this matrix into two new matrices, users matrix and items matrix, U and V. Now, look at these dimensions, M by D and N by D. Now, the whole idea now is I want to crunch this millions by millions, dimensionality into a way smaller, or into a lower dimensions. So D in this case here, if you look at the new matrices, will be M by D and N by D. D in this case is way less than M and N. So think of D in terms of hundreds, like 100, 150. From millions, you want to like crash down the dimensionality into 100 or 150, 300, but it's not millions for sure, right? So the whole magic here is how can I come up with those two matrices, U and V, and at the same time, I don't want to lose actually the actual ratings. So the whole idea here is I want to come up with those two new matrices with low dimensionality. But those two matrices, if I multiply them together, I should be able to regenerate this matrix. So that means a rating of X, which is 4.5. If I now multiply those two matrices, I should be able to regenerate or reproduce this value. Not exact, if not exact, the error rate should be low, So this is the idea is you have now a rating matrix. You want to now regenerate out of that two new smaller matrices in terms of dimensionality. And those two smaller matrices, the visitors and the users and the items, once I multiply them together, then all those actual ratings from the users need to be estimated almost the same or very close to the actual ratings. The other thing that's going to happen in this case is, guess what? All those empty or blank spaces with the new dense matrices that I have, they're going to have estimated values as well. So basically it becomes that, okay, if I would like to estimate now if user A would like the movie W, all I need to do then is take this row of A and this row of W, do the dot product between the two vectors, and then boom, I have now the estimated rating of A to the movie W. And same thing with the other empty spaces here. So this is the idea of the matrix factorization. Take rating, split it, make sure that you can regenerate. This is how the training happened, that you want to minimize the error of regenerating the same matrix again. And this leads us to this slide, which is the target function. So with matrix factorization, the target function is to minimize the error rate of regenerating the actual rating matrix from the two matrices that we try to generate with low dimensionality or in the latent space. So basically, this is like the predicted rating, or this is the actual rating, and those are like the dot product should give you the predicted ratings. And what you need to do is you need to minimize the difference between the actual rating and the predicted one. In order to actually optimize this function, what we need to use optimizers. And in this case, the most popular tool for this problem for matrix factorization are stochastic gradient descent and weighted alternating least squares. So if you choose to go with the stochastic gradient descent, which is very popular in most of the deep learning techniques for optimization, then basically the pros for this technique is it's very flexible, which means if you want to come up with a different loss function, not this one, not exact one, then it's okay, it's going to work. Also, it can be parallelized. But the cons of the stochastic gradient descent, it is slower when compared to the weighted alternating least squares. So the weighted alternating least squares, on the other hand, the pros is it can be parallelized. It converged faster than the stochastic gradient descent. But on the other hand, the cons, it is not flexible. So it cannot handle other loss functions. It was designed mainly for this loss function. So again, to summarize matrix factorization, you have rating matrix. The goal, it's very sparse, it's high dimension. We want to now bring it down into lower dimensions by splitting it into two matrices, one for users, one for items. The training is going to be to minimize the loss, which is in this case, to regenerate the actual ratings in the matrix and make the error rate minimal. And once it's converged, then basically to predict the ratings of any empty cell here, you need to take the vector of this user and the vector of that item, dot product, boom, you have the estimated rating. Any question at this point before we move to the factorization machines?
No questions, Khalifeh.
Good. All right. So let's talk about the factorization machines.
Oh, there is just one popped in, sorry. This is from John Tardy. Actually two, just one other one just popped in. On the matrix factorization slide, can you walk through how the math works to get the original number?
Where, here?
On the matrix factorization slide, yeah.
Yeah. Yeah, so if you take now this A and W, right? So you take A, it is 1.2 and 0.8, and you do now the matrix multiplication with W, which is 1.5, 1.7. This is the transpose of the matrix because the matrix multiplication used to happen. So it is 1.2 times the 1.5 plus the 1.2 times the 1.7, and then 0.8 times this plus 0.8 times that, if I still remember like the matrix multiplication equipment. But this is how that multiplication is going to happen, and then you end up with a value that actually represent the what the rating should be in this spot.
Okay, and then another question from Carlos. I'm not sure if you kind of just answered this, but what is the technique to transform matrix to user matrix and item matrix? Yeah, that's what you just went through, right?
This is what we are talking here about, the target function. So the target function is going to basically do this magic for you. Okay.
And that's it.
All right. So the factorization machines, in this case, let's deep dive into factorization machines. For factorization machines, what is the problem with matrix factorization? Maybe it seems perfect, right, when we describe it. But the problem with matrix factorization, it is not a general predictor, right? Which means it was designed mainly to kind of that fill in the blank problem, which we described. I want to predict actually the missing ratings in a matrix. And I want to split a matrix into two matrices and basically regenerate the actual matrix. So the factorization machines was inspired by the support vector machines. And maybe this is where the name came from, right? So support vector machines is basically a generic predictor, and it is one of the most popular and successful predictors that we have in machine learning. So factorization machines came actually as or inspired by SVM in a way that they wanted to extend the idea of matrix factorization, the factorization aspect of it, to actually become a general predictor. So that's where the factorization machines idea came from. So if you think of factorization machine, it's a model class that combines the advantages of support vector machines with factorization models. It's actually, the idea here is you model all the interactions between variables using factorized parameters, and then the factorization machines can handle very sparse data sets. SVM will fail if it trained with sparse data sets. That's why like factorization machines came to solve that problem for SVM as well. And factorization machines is generally predictor just like SVM. With that in mind, down the road, when we go to the deep learning techniques for recommendations, you will notice that deep learning techniques for recommendations mainly try to actually leverage the factorization machines. So you will see deep factorization machines, extreme deep factorization machines, and so on. So this is very important. That's why I put it here, because we're gonna later actually revisit the idea with the deep learning approaches. So let's look at the factorization machines here. let's build our vocabulary and definition here. Those columns in this data set now becomes fields. So this is how we call them. And then the values of those here, we call them features. So each value is a feature. And then this is the target variable that we try to predict. So in this case, as you see, this is not the same setup we have for matrix factorization, where you have ratings and there is like empty cells that you need to predict what is the rating, what would be the rating in those cells, right? So this is different setup. And this is usually what we see in most of the machine learning problems, that you have a target variable and you have a list of features and you need to predict that target variable, right? So with that in mind, keep that in mind, then Factorization Machine has two actually versions. One of them is Factorization Machines, the original paper that I put actually here on the right side. And there's another version called Field Aware Factorization Machines, FFM. So the difference is that the field aware actually, it takes into consideration the column interactions. So instead of just the values interaction, the features, it takes actually the fields interaction as well into consideration. So that's why it's called Field Aware Factorization Machine, FFM. Now, there are 3 different libraries in Python where you can actually implement the factorization machine or leverage factorization machines and field aware factorization machines. The libfm has actually the implementation of factorization machines, but not libffm. Xlearn is another library that has the implementation of this technique. Field aware FFM, you can find the implementation in libffm and in Xlearn, but not in libfm. Overall, as you can see, Xlearn is the most recent actually library that was released that has the implementation of those both. So we highly recommend that you use the Xlearn. Also, if you are looking for data sets for this click-through rate problem or for the movie prediction, the ratings, then the most popular ones, or not the most, but actually among the most popular ones are the MovieLens and Avazo. Avazo is actually not as popular, but MovieLens is definitely one of the most popular. Avazo is a click-through rate prediction, so similar to this setup for ads. So if you would like to play with a data set, publicly available data set, and test those algorithms, then you can use the Xlearn library and you can use those data sets. So closing up on the collaborative filtering, the pros and cons of this technique. The pros of the collaborative filtering, the first thing is serendipity. Serendipity means that with collaborative filtering, actually, you can surprise users with things that they didn't think of. Because again, you use other users who maybe did discovery and they discover new things and they rated those things higher. And then the customer wasn't aware, or the user wasn't aware of that movie at all. So with collaborative filtering, serendipity is there. And it is a very important aspect actually in recommendation, because people sometimes get bored of like you keep showing them similar things. So they need to change or discover new things. And with collaborative filtering, you get that advantage. A great starting point if you plan to do recommendations or recommender system in your company. No feature engineering is needed. That's another thing, because basically all you need is you take the users and their feedback and the items, and you can go ahead and start implementing that. Cold start problem is one of the first cons of the collaborative filtering. And again, the definition of cold start problem is if you have new users or if you have new items in your inventory, then you don't have interaction between the users and those items. In that case, you cannot generate recommendations. So the new items will not be part of any recommendation. The new user will not receive recommendations until they start interact with the system. Sparsity, as we described, and we said like matrix factorization is there to solve the problem of sparsity. Popularity bias is there. It is still there. So popularity bias, popular items will usually dominate the recommendations, and it is hard to enrich other features, which means, let's say from the domain knowledge, you know that the director of the movie or the freshness of the movie makes difference and makes it more attractive to customers to engage or watch. So you cannot actually easily enrich your collaborative filtering algorithm with those external features. All right, with that, we're moving to content-based recommendations. So let me just see how we're doing with the time. I think we're good, because we still have lots to cover. So with content-based recommendations, the idea here is, instead of relying on other users, interactions and ratings and selection, I have the user engaged with an item. I want to now go and take that item, and I want to actually find similar items by basically looking into the content, the features of that item itself. I don't want to look at what the other users who watch this movie or bought this item, what they did, what are the other items they bought or they liked. I want to use this exact same item here, in this case, avatar, and see from the features of avatar itself, can I find similar items and then recommend those similar items to the user. So in this case, you see only one user in the slide. There's no 2 users, 3 users, because I'm going to use only the what this user is like. So some of the features that you can think of when we talk about movies: the genre, the actor, the director, the duration. So I can take all those. Definitely, you can think of others, and you can use those to find similar items, similar movies, and recommend them to this user. So that leads us to the discussion about features engineering. So given that you need to come up with those features to actually measure similarity between items, then you need to do features engineering. And features engineering is kind of sometimes tough, because when you have a large pool of features, you need to do the features engineering right. Otherwise, your models won't learn. So features engineering requires domain knowledge. And in this case, you need to know actually what are the features that matter, what are the features that doesn't matter. Some data scientists do some tricks by, okay, I'm going to take those bunch of pool of big features, big pool of features, and I'm going to go, for example, implement decision tree and see the importance of the features in the decision tree. So some tricks need to be applied there before you decide what is the set or pool of features that you want to use to train the model. So anyway, if you have we have 2 types of data that you can use with content-based recommendation: structured data, and in this case, it's tabular data like this, which basically gives you the movie name, the genre, duration, overall rating, director, price. So if it is tabular data, if it is structured this way, then this is what we refer to as structured data. And this is what we said, you need domain knowledge actually to come up with those set of features, and they need to be actually provided, because if for example, you said, okay, actually, genre is very important, but genre is not given. You know, they don't have a classifier to classify those movies into genre, or they don't have even manual annotation of those genre, then you cannot use it. So the feature, you decide about a pool of features, and you need to make sure that the values are there, it's given. And the coverage of this feature is there, because it doesn't make sense to pick a feature that actually covers 10% of only 10% of the items in your inventory has value for this feature. All right, so another problem we face with the structured data in the features engineering is for those categorical features. Categorical features, features that actually has string values, they have wide range of potential values. For those ones, we have actually to do some kind of encoding. So one popular way is the one-hot encoding. So in this case, if I want to generate one-hot encoding for this director feature or field, in this case, what I do is I take all the possible values as kind of vocabulary or index. And then if I want to now do the one-hot encoding, so Cameron is number 1, Wachowski is number 2, Shelter is number 3. Then for the one that has Cameron, it is 1 in the index of Cameron, then zeros in the others. For the other one, it is 0 for Cameron, 1 for Wachowski, and then 0 for Showalter, and then 001 for the third one. So this is how you transform the features from categorical to numerical, because machine learning models needs to consume numerical values, numerical features. And then same here, you can transform those categorical features into numerical features the same way. So that's one also of the things that you need to do, transformation, features transformation, as part of the features engineering. When it comes to unstructured data, the unstructured data, assume now you work in a company where they just have the movie description. They don't have luxury to provide those, extracted features that we're talking about. So you have only plain text that describes Titanic, only plain text that describes Transformers, right? So if that's the case, then with unstructured data, and this is what we refer as unstructured data, it's a plain text, images, all those are unstructured data. So if that's the case, then we rely on embeddings. So when it comes to unstructured data, the first thing that we should think of for content-based recommendation is embeddings. And embeddings is actually, the embedding space is a low dimensional and it captures some latent semantic structure. So if you think of the text, think of each word as a dimension. If you want to take this whole paragraph now as features, each word in this paragraph is a feature, right? So it's a very high dimension. If you think of a document with thousands of words and tens of thousands of words, then each word is a feature. It's high dimensional space. And as we said, in high dimensional space, there is a sparsity, and machine learning models usually don't learn. So you need to crunch it down into low dimensional space. And that's what embeddings give you. So the embedding space is low dimensional and it captures some latent semantic. So similar items such as videos that are usually watched by the same user end up close together in the embedding space. That's basically what turned to happen. So if you actually generate embeddings of those textual features or the description or the title, or even if you generate embeddings of the image using like convolution neural network or whatever, then it tends to happen that if they are similar, they will be close to each other in the latent space. All right, so with that in mind, then how can we actually generate the text embeddings if we are talking about now the unstructured data? So you have the very traditional way, which is the bag of words, a very naive way. And in the bag of words, the documents are represented as bag of words, which means the order of words is not preserved. And that's the first problem with the bag of words. So 2 weeks ago, I think the session was NLP. So I believe that most of the stuff was covered. That's why I'm going to just go over it quickly. And then the other one is TF-IDF, and the term frequency inverse document frequency. It's another technique that can actually identify the importance of the word in a document, and then the document would be represented as a vector of those like words with their weights or importance, and then you can basically measure the similarity between those vectors. The third way, and now we're talking about the neural network-based approaches, Word2Vec, which was introduced in 2013, and I put deep learning in parentheses because actually deep learning in quotes, because deep learning, maybe there is a debate in the community. It's actually shallow network, it's not deep. So, but it is one of the most popular deep neural network-based models for text embedding. And it considers the context, so it learns actually the semantic of the word, and it reduces the dimensionality while maintaining high accuracy. It was introduced by Google researchers in 2013. Glove, on the other hand, which came as an improvement over Word2Vec in 2014, referred to global vector of word representation. So those are the techniques that you can use actually to generate embeddings of the document. And in this case, it's vector representation of the document. And then you can apply cosine similarity or whatever to find the similar content or the similar items, which you can recommend through the content-based recommendation system. All right, pros and cons for the content-based recommendation system. Content-based recommendation system, it's easy to scale up. It's not like the collaborative filtering. We said you have like a huge matrix with a sparsity, blah, blah, blah. With content-based recommendation, usually it is easier to scale up. Also, it doesn't have the cold starter problem because again, you're not relying or waiting the interaction between the user and the item to happen before you are able to generate recommendation. So as long as the item has description, title, it has some features, you can generate recommendation. For the new items, for the new users, the same. If they have profile, you can generate recommendations. And it gives opportunity to list popular items. We said collaborative filtering is biased towards actually the popular items. With this technique, with content-based, you actually give a chance, an opportunity to the least popular items to appear in recommendations. On the other hand, on the cons side, there is no serendipity, which means I will always keep recommending similar items or similar stuff to the anchor item that I used at the beginning. So there is no serendipity. Also, it requires features engineering, as we discussed, and it requires domain knowledge. So those are the cons of the content-based recommendation. Cool. So before we move to the deep learning models, I would like to take any question at this point.
Okay. We have a couple. One of them is a little bit was from a section ago, but I think you make sure you covered this. Is it possible to adapt the matrix factorization technique to make predictions for users who haven't made any ratings yet? Like if the row is missing?
No.
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 There you go.
Yeah, that's a cold start problem for what we refer to user cold start problem. Yep.
Okay. Jeffrey has a question. Glovey seems to be is it glove or Glovey?
Glove.
Seems to be embed individual words. How would you use to embed an entire document?
Yeah, great question. There are actually different ways to do that. So you can take the average of the words in the document when you generate the embeddings of the whole document. There are already, by the way, other techniques that give you the embeddings at the document level. One of them is doc2vic. Instead, it's an extension of word2vic, doc2vic, and there is also fast text from Facebook, which was released back in 2016, I believe. So fast text from Facebook, it can actually take the document and generate embeddings for the whole document. But usually, even those, like what it does, it takes a glove or word2vic at the word level, and then we take the average of the embeddings of all the words, and that's become the embedding or the vector representation of the whole document. So you take all the vectors, you take the average of all these vectors, and this average vector now is the representation of the document.
Okay. And then Aaron Cook has a question. Should we use AI to determine items in images and use that to check for similarities in higher watches or views?
Great question. It's possible. So we actually, I think towards the end of the talk, I'm going to present a use case from Home Depot, and I can give some insights about something we are doing in that regard, which is extracting like objects from the images and measure the similarity according to that. So yes, it is possible. It's very challenging though, and because it requires actually like multimodal learning. In this case, you need to learn from the image and the text together. So I'm going to present something aligned with that towards the end of this talk about a use case within Home Depot.
Okay, those are all the questions for now. Thank you.
Great. Okay. So moving forward, let's talk now about the deep learning for recommendations. And the first, and I think the most popular thing that we, in the research community in the recommendation system that we find very interesting, wide and deep learning. And wide and deep learning is a model that was introduced by Google in 2016. So the name actually is interesting. As you can see, wide and deep learning, right? So if you think of now a linear model, linear regression, logistic regression, this is what they refer to as wide. So the linear model in this case is the wide. And then deep is basically deep neural network, okay? So this is the reason behind the name. So basically they combine, it's hybrid. So they combine a linear model with a deep neural network model in the same learning. So they train the two models in parallel. And you can see here in the diagram at the above, the one in the middle, this is actually the wide and deep. So you see, this is a linear model at the bottom. And this linear model, as you can see, it's directly connected all the way towards the sigmoid layer, right? So this sigmoid layer, in this case, it's gonna update the weights for both, for the deep neural network and for the linear model, if it is linear regression or logistic regression, because again, they both assume stochastic gradient descent as their optimizer. So this sigmoid layer then is gonna basically optimize the weights for both, for the linear model and for the deep neural network in parallel. The benefit you get out of that is the following. It turned out that linear models are very good at memorization. And we mean by memorization, if you have a very specific query, let's say you said, I want, and this is from the author's blog, I want a decaf latte with half milk or low fat milk. You are very specific about what you want, right? In this case, deep neural networks tend to generalize, which means in the latent space, and I put examples towards the bottom of the page here, the slide, in the latent space, as we said, based on the embeddings that comes from the neural network, it's gonna actually put this decaf latte with half milk or low fat milk very close to latte whole milk, okay? Because based on the latent semantic and the context, they are similar, right? So it could be that when you requested that very specific thing, and that it's gonna, because it's generalized, it's gonna take that, generate the embedding, and find the most similar item is the latte with whole milk, right? And return that to you. So when you are very specific, the idea is we want to give you exactly what you requested. We don't want to use the magic of the embeddings and serendipity and go find similar things that is not exactly what you requested. But on the other hand, if you are generic in your request, you said, I'm interested in coffee, right? Or latte without specifying anything, latte. Then it makes sense now to go to the, instead of use the linear model and get you exactly just latte, it makes sense now to go to the deep learning model and say, okay, now what are the similar things to latte? And then we're gonna show you a wide range of things. And in this case, the example from the author's blog from Google is that if you are interested in a fried chicken, right? Fried chicken. So fried chicken, if you look at the other like things that closer to fried chicken in the latent space, there is chicken and waffle, there is burgers. So you may accept it if you just said, you know, I want fried chicken. And then the recommendation came with chicken and waffle burgers, then, oh yeah, why not, right? But if you are very specific, I want, you know, fried chicken and that's it. Exactly fried chicken. I don't need burger, or then the deep neural network again might mistake your order and get back to you burgers or chicken and waffle, but the linear model will not do that. So this is the idea between combining the linear model and the deep neural network models together. Is the linear model gonna always maximize the memorization, and the deep neural network gonna provide the serendipity and the generalization. But that's the whole idea of the wide and deep learning approach for recommendation. So, okay, questions about wide and deep before we go to the deep FM?
There is a question. This is from Shital. Two questions. He has two questions actually. Do you recommend Surprise, which is a Python scikit for recommender system, especially for collaborative filtering system?
To be honest, we haven't used it, so I cannot actually say yes or no. I cannot recommend it, but yeah.
And the second part, what are some good techniques to develop a collaborative filtering recommender system when you have big data sets? I'm dealing with 8 million rows of structured data in my project.
Yeah, I think as we said, like that's a challenge definitely in collaborative filtering. So matrix factorization tend to help in that scenario. The other ways to handle it is some of those deep learning approaches that we're talking about here. So hopefully the other techniques that we're going to present towards the end can help in answering that question, especially the deep factorization machine and deep FM and the extreme deep FM, because they tend to solve this problem at scale.
And then last question from Ryan. Do you primarily use TensorFlow or PyTorch?
We use both, primarily TensorFlow, but we started recently use PyTorch as well due to some benefits that our data scientists find in PyTorch, especially the flexibility and the easy to implement. I mean, if you use Keras with TensorFlow, to be honest, I don't think it's a big deal for you. But if you use TensorFlow directly, then you will find some benefits in using PyTorch as well. So we use both, but if I would give like percentage of where we use TensorFlow versus PyTorch, it's almost like 80% TensorFlow, 20% PyTorch.
Okay. Yep. Those are the questions for now.
Great. Right. So moving forward with the deep factorization machine. So again, wide and deep, we understand here the benefit. It's I have linear model that can actually memorize for a specific questions, and I have the deep neural network model, which can generalize and do serendipity in the recommendation. And combining both of those, you usually have, you can kind of cover both cases when people are very specific and when people are more generic. So with DeepFM, again, this was introduced 2016, wide and deep learning, and this is usually what happened in the research community and recommendation. A new model will come, a breakthrough model will come out. Then the researchers start, iterate over and identify the issues, the problems, and try to solve them in the next version of this model. So wide and deep came from Google 2016. Then those researchers who did the DeepFM, they looked at that model, they identified actually where is the opportunity. And the opportunity was that factorization machine, as we said, it's very powerful and useful model, right? Especially when we talked about the matrix of features, and I would like, without lots of features engineering, I would like actually to do the predictions of the target variable. So the DeepFM is trying to solve the linearity limitation of the factorization machine. Factorization machine at the end is linear. So what they try to do is to add nonlinearity to factorization machine. Why you need to add nonlinearity to factorization machine? That's the question. So in factorization machine, the model is gonna learn the interaction between the features at low order. We mean by low order, this example. So let's take about recommendation on the mobile, on the App Store. So male customers, teenagers male, tend to like the shooting games, okay? So if you take that, now you have three features interact with each other. You have the gender, you have the age, and you have the category of the app. So those are three together engage or interact to make the prediction one, which is yes, they're gonna click. If I show them recommendation of shooting app, they're gonna click, right? This what we call order 3 interaction, because it has three fields or features from three fields that interact with each other. Low order features interaction, which is the original factorization machine do, is at the level of 2. So order 2. And the order 2 in this case means I only look at the two features at a time, the interaction between them to predict the value. So you limit yourself in this case to only 2, because if you want to go beyond 2, it becomes computationally very expensive and the model may actually not converge, right? So it's like a challenging to scale up FM to actually beyond or high order interaction. So DeepFM came to introduce, to take the idea of wide and deep, and instead of use linear model like regression, linear regression or logistic regression, they said, no. Let's take the FM itself, factorization machine, as our now wide model, and let's add the deep neural network and train both of them together. Their idea here is that by doing that, we're gonna allow high order interaction. So in this case, the example I gave, the three features interaction is possible because the deep neural network actually is very good at modeling those interactions at scale. So that's the whole idea of the deep FM. And if you look here to the design on the right of this deep FM, the fields, if you remember the table when we showed the field are the columns and the features are the values. The fields will go, first of all, we said we convert everything to numerical value. That's the input. And then they go through the embedding layer. And after the embeddings, then what we do is those embeddings actually go to the factorization machine and the regular factorization machine. And the factorization machine gonna do its thing, which is usually like the low order interaction training. And then the result or the output of the factorization machine gonna contribute to the output from the deep neural network. So all the embeddings gonna feed both the factorization machine and the deep neural network, and then those two models gonna contribute to the output layer. So that's the deep FM. It came back in 2017. The whole idea here is they want to expand the factorization machine, the FM, beyond the low order interaction. They want high order interaction, plus they want to add nonlinearity to it. All right. Now to the extreme deep FM. I don't know. Did we receive any question, Tommy?
No, no questions right now.
Okay. So extreme deep FM, X deep FM, and this is one of the algorithms that we actually implemented and tested for one of our collaborative filtering recommendations. So extreme deep FM, the X deep FM, with the deep learning here back in the deep FM, again, look at the sequence, like 2016, wide and deep, 2017, deep FM, 2018, extreme deep FM. Again, the researcher is gonna look at the shortcoming of the previous model. They try to introduce a new model. So what was the shortcoming of the deep FM? The shortcoming is that deep FM, the deep neural network part of it, it's gonna actually model all the possible interactions, the useful and the useless ones, you know? So the features, whatever combination makes sense or doesn't make sense, it's gonna actually model all the possible interactions, which they claim that actually that's bringing noise. Okay, so this design of the extreme deep FM, X deep FM, is actually the first thing to avoid the modeling of useless feature interactions, sorry. And then the jointly learns explicit, this model jointly learns explicit and implicit high order feature interactions effectively. The main difference here is that you're gonna actually keep feeding the neural network here. It's a new design, they call it CIN. And this new design, the CIN, is actually keep taking the input from the original matrix embeddings, or from the original matrix, the input matrix. So they keep receiving embedding throughout all the hidden layers. It's not just you give it to the input layer and then you stop, and then you let the network actually figure out everything by itself. No, it's actually you keep feeding those input vectors or embeddings into each hidden layer in the network, in this CIN. And the goal here is, again, they try to influence this network, the CIN, by always introducing what are the original, you know, embeddings. So you always kind of influence with explicit interactions. So this is the difference from the learning perspective. It requires no manual features engineering, no matter what, you know, so whatever feature matrix you have, you can feed it as is. And then interactions are applied at vector-wise level, not a bit-wise level. And that's another important difference here. So they don't look here at, if you think of the deep learning in the original one here in the DeepFM, here, this part, which is the deep learning part. Usually the hidden layer, we always think of deep learning as black box. So always those layers, they're gonna actually take the embedding, the vector representation, and they're gonna actually try to, at the bit level, which is like each dimension of that vector. So assume you have 150 dimension in the vector. So they take each of those inputs from the vector, the 150, and they use it in the optimization, okay? But here at this design, what they do is actually they take the vector, the whole vector as is. They don't take the bits inside the vector. So the optimization happen at the vector level. And that's another important difference here, which they claim that actually avoid the interaction between the dimensions of the vector itself, because they believe the neural network in the original DeepFM, it's gonna even optimize the interaction between the dimensions of the vector itself. So here they said, no, we're gonna do it at the vector level. It's not a bitwise level, it's vector-wise level. And then high order feature interactions is measured explicitly. And how they measure that explicitly, it's they prove in their paper that each hidden layer in their design of this CIN actually increase the number of, or the order of the interaction. So the two order interaction, the order 2 interaction is going to happen maybe at hidden layer 1, then at hidden layer 3, if they add that layer, then it's going to start implementing the or modeling the order 3 interaction. If they add 4th layer, then this is be the 5th order interaction, and so on. The complexity of the network will not grow exponentially with the degree of interactions. That's another difference with DeepFM. So overall, this is kind of the recent implementation of the or extension of the factorization machine, extreme deep factorization machine. Every one of us now, after hearing all that, wide and deep, DeepFM, extreme DFM, XDeepFM, would ask a question: which one should I pick? Which one is better? And here's the good news. So we did benchmark between those models on the open data sets, MovieLens and Avazo. And here we measure the performance based on the RMSE, so lower is better. And here we measure the performance as AUC, area under the curve, and this is higher is better. So as you can see in both use cases and with both metrics, the XDeepFM actually outperformed the other ones. So it is 0.9 the RMSE, 0.9 for XDeepFM, and the AUC for XDeepFM was 0.785 compared to the other models. We started with 0.775, we end up with 0.785, and as you know, an EOC closer to 1 is better. So XDeepFM was a clear winner on both data sets and in both cases. And as I said, actually, we implemented XDeepFM for one of our collaborative filtering problems at Home Depot. So it actually does what it promised. It's actually scale up, and it is delivering relevant results. Questions before I move to the Home Depot use case? And
yeah, we have a couple. So hopefully I'm reading this correctly. Does all deep learning require feature engineering? Because in regular supervised, feature engineering is big challenge in selecting features.
No, not actually. Most of them said, okay, what you have, you can feed all of them, and that's the idea of the DeepFM and XDeepFM, especially that they're gonna actually figure out which features matter and which features not by taking the interaction between all the possible interactions between the features into consideration, and then the network will decide actually at the end which features matter, which features not. Again, it's going to be black box, but you don't need to do features engineering before you feed it into the network. So you can feed the features, the plain features as is.
Okay. And then we have a question here. Ryan says he's confused about CIN. Can you maybe rephrase?
Where's CIN? CIN here?
I think so. See, Ryan, can you elaborate maybe a little bit if you can hear me? CIN.
CIN is, yeah, this is again like this.
Okay, there you go. Yep.
CIN. Yeah. So CIN is basically, I put here like zoom in into the CIN design. It's a new network, neural network. It's referred to, I think, a cross interaction network. That's why it's CIN. It was introduced in this paper for XDeepFM, and the resources are at the end of this presentation. It was introduced there. And the idea, it's combining ideas from RNN and from convolutional network, CNN, in order to basically influence or make sure that the vector-wise interaction is maintained and it's not bitwise interaction or bitwise level. The interaction are at the vector-wise level, not the bitwise level. So this is what the CIN is doing here. And as I said, if you look here at the zoom in of the design at the bottom, you can see that the original, like the input matrix X0, this is gonna be always feeded all the hidden layers. It's not just you feed it to the first layer and then the input layer, and then the hidden layers will receive only the output of the previous layer. You add into the output of the previous layer actually the original input matrix, and that was the difference in the design.
Okay. And then so he follows up. So it's residual. So it is residual.
I'm not sure if it's residual or not.
Okay.
Yeah.
And then
but I
Jeffrey
put the reference to the paper at the end, so he can actually go to the paper and answer the question.
Okay. And then Jeffrey has kind of a question on this slide as well. The last step of the extreme deep FM seems to combine several model and outputs, linear, CIN, DNN, to a final stage output unit.
Right.
How do you decide how to combine these? Is it determined with the same gradient descent techniques you use to train those models?
Yes, it is. Again, if you look here at the design, so if you think of the back propagation, it's optimize all of them, right? So it's going to optimize all these models in parallel. So at the end, when you train the network, it's going to actually optimize all these models in parallel. So in this case, you don't need to choose. This is part of the design of the network. So it's going to actually combine the results based on the optimization that it reached when it converged between the linear, the CIN, and the plain deep neural network.
That's it for now.
Okay. All right, so let's take now an actual use case from the industry, which is from Home Depot. And this is actually a work that we published last year at ACM Rexis conference, which is the top recommender system conference. And the idea here is the following. So when you come to Home Depot, we are a home improvement retailer, and you expressed interest in bath vanity. We have the bath vanity, we have the description of it, the title, the model, the brand, we have all these features, and we have the image of it, right? So at the end, what our recommendation is supposed to do is to show you all the other items that can complete your bathroom that match the style of this vanity, the color finishing style, you know, and its complement function. So I don't need to recommend another vanity to you. I need to recommend, like in this case, the vanity is here. What about the vessel sink, the bath lights, the toilet, the linen storage cabinet? So if you think of that, and the mirror, if you think of that, you start with an anchor item. This is what we refer to as an anchor item. In this case, it's the bath vanity. And our recommendation algorithm is supposed to figure out what are all the other products that we should show you to complete the look of that bathroom, or to complete your shopping for that bathroom. So this is the problem that I described, and this is how we solve the problem. So in this part, we highlighted the deep learning model that we built that actually use the textual features. So let's take now on the left here, I have the collection labels, as you can see. So how we train our network. So in order to train deep neural network, usually you need to have supervised data, right? Labeled data sets. So for our collection, when we train this model, so we looked at, on our website, there was kind of manually created and curated collections before. So I see that this actually chair with those set of chairs, they form collection, yes, so the label is 1. Those 2 chairs with the couch here, yes, they form collection. How about this chair and this chair? No, 0, they don't form collection. So we started with that kind of manually labeled data set by our in-house domain experts, merchants and others. And they provided us with this data set. So what we did then is, okay, we took those positive and negative examples, and we came here. We said, okay, so give me the title and description. We're talking here about the text of the product A, and give me the title and description of the product B. And let's think now of this chair at the top as A, and the chairs, the other picture, the lifestyle image, as B. Cool. And in this case, we also give example from the faucet and the shower head, if we're talking about the bathroom collection. So I take input product A, product B, then we send them to embeddings layer. After that, what we do is we have bidirectional LSTM that takes both embeddings, the embedding of A and the embeddings of B. And then here we generate the vector of B, vector of A. And then here there is cosine similarity layer here, where we measure the cosine similarity between now the 2 vectors. And then we predict if this label is 1 or 0. And if the actual label is 1 and we predicted 0, then this is actually during the training, the back propagation gonna happen, update the weights of these two networks in parallel. And then when the network converge actually, at that point, you can take this network and start feeding into it any two products that is not part of the training data for sure. And then the network is gonna spit out 1 if they should belong to the same collection, or 0 if they should not belong to the same collection. And this is what you then use to generate the recommendation. So for each anchor product, in this case, back to the examples, this bath vanity, I'm gonna take it as an input here. And I'm gonna go to the categories that of the toilet mirror. And there is another story of how we decide about those categories. There is another machine learning model behind the scene that decide about those categories. And I'm gonna take each product there. I'm gonna say, does it go form a collection with this input? So the input is gonna be the anchor, and here a potential recommendation. And then the network gonna say, yes, you can recommend it, or no, you cannot recommend it, with definitely a relevancy score, right? So this is cool. This is what we did with the text. What is not in this slide is actually what we did with the image. Because again, if you look here, the visual are very crucial. I need to match the color finishing. So for that, what we did is we used the computer vision algorithm to generate, again, representation, vector representation of the image of the product in terms of the colors that appear in that product. So in this case, the black and the brown colors, the representation, the vector representation of those colors gonna represent this bath vanity. And then what you do is you generate, again, the vector representation of the potential recommended item from the image that represent the visual features, the color finishing. And then you have to measure the similarity by the dot product. And then you have then score based on the text matching, and then you have a score based on the image match. And what you do is you then have a linear equation, weighted linear equation, that actually decide how much weight we should put on the visual matching, how much we should put on the textual matching. And then you can combine those two scores. And this is what we refer to as multimodal learning, because you learn from text and images at the same time. The question become, after you generate those vectors and embeddings, how would you serve recommendation into the customers, right? So you have now, you did whatever, DFM, XDFM, or the model bidirectional STM that I just showed. At the end, you have vectors that represent the products. In this case, we're talking about the Home Depot products, right? So I have an anchor product, and I have a pool of millions of candidate products that I can select from. Which one? How can I pick the top similar items that I should show this product, right? This is where the KNN comes into the place. So usually what you do is, after you generate the vectors, is you take the query vector, we call it, and then you have the candidate vectors, the pool of candidate vectors to match against. And you need to apply KNN. But if you think of the KNN implementation, think of KNN at that scale, that you have millions of anchors and you have millions of potential recommendations, and you need to do the KNN at that scale. So definitely it's very challenging, and KNN as is will not scale up. So there are, luckily, open source libraries that we actually evaluated for our use case at scale. And so we evaluated FACE, which is a Facebook library for large scale KNN, and NOI, which is a Spotify library for large scale KNN. And it is funny about the name. And NOI is actually approximate nearest neighbor. But what is the OY? It is oh yeah. So approximate nearest neighbor, oh yeah. This is from Spotify. And then NMSLib. So after evaluating all these candidates libraries for large scale KNN, it turned out that NMSLib is actually the best performing one in terms of accuracy. So we ended up using NMSLib for our problems. So this is almost the last step usually after you generate the potential or the embeddings, the vectors from the deep neural networks. At the end, you need to do KNN between the query vector and the candidate vectors. And to do it at a scale, you can leverage one of those libraries. And with that, I put here the resources to most of the stuff that I covered today. And thank you. We'll be happy to answer any question in the remaining time.
All right. Yeah, we have a couple questions that just came in. So does this setup of deep learning network have any assumptions or weaknesses? For example, CNN has a weakness that the variables and dimensions have fixed limits, which makes them poor with some time series data that can have a wide range of values. Markov chains weakness is that they take data that is not Poisson or exponential distribution like COVID data. So I'm not sure if
So
you got
all these deep learning models, same thing. They assume that the embedding is gonna have at the end the same dimensionality. So the same. So you are limited to the same dimensionality for all the embeddings, right? That's one way. And when we discussed each of them, actually we discussed the limitation of each of them. So for example, with the FM factorization machines, again, it's for low order interactions. So you cannot go beyond 2 usually. Most of the implementation of factorization machines stop at 2, order 2. And then for the deep FM, the limitation there was that you don't have control over the interactions because it's going to calculate the useful and useless interactions, and that's might bring noise, right? So each of them has its own limitation, and that's why every time, as I said, like the researchers will find the shortcomings, the limitations, they will implement an extension that solves those problems. But from the embeddings perspective, all of them assume that all the embeddings needs to have the same dimensionality, the same dimensions, and that's for all the deep learning models the case.
Okay. John Tardy has a question. So for the Home Depot use case, is recommendation based on content and features of the products, but does not use the behavior of other buyers? Is there a reason for that?
So Home Depot has, if I would say, probably 34, 35 recommendation algorithms on the website that power the recommendation on the website. So what I presented is one of them that is content-based. It relies only on the features of the product. We have many others that actually leverage the customer behavior. Like the first one I put in the slide, frequently bought together, right? And even the one I just showed for the deep learning, I said we have machine learning model that decides which categories we should build a collection from. Those categories actually, the algorithm behind the scene leverage the customer's behavior as well. So we have leveraged customer behaviors a lot. We rely on that a lot in terms of views, purchase, you know, all of that kind of behavior. We leverage that a lot. And as I said, like we have more than 34, 35 algorithms that serve recommendations on the website. So it's not just one single algorithm.
Okay. We got a question from Carlos. What do you think about using more like this feature that some search engines have as a recommendation system?
Yeah, I think the more like this, again, it's content-based, right? And we have it even our website, it is content-based. It has the same limitation of the content-based that, I mean, if you put it at the right place from the customer perspective for the customer experience, it's usually good to have it, but you need actually to do user research and see where it makes sense to have it. But it's content-based, and content-based again has its own limitation that there is no serendipity, and usually it relies on the quality of the, especially if it comes from the search engine, it relies on the quality of the textual features that are stored in the search engine, the schema of the search engine itself. So those limitations are there. So if the test shows that it is useful, then definitely why not? And again, we have it at Home Depot. We have them more like this.
Okay. We got a question from Ryan. Hopefully I get this correct. So the data set for the bidirectional Siamese, maybe this is supposed to be items.
Yeah, Siamese network. Yep.
Okay, is a supervised task for items that are known to be similar? That's a question.
Yeah, it is supervised. As I said, like we started we trained the network using manually labeled data set from our in-house experts. So it is supervised. It was trained using manually labeled data. Yep.
Okay. And then Jeffrey has a question for the Home Depot collections example. How big do the human-generated collection labels data set have to be in order to build a good deep learning model for the whole store?
That's a great question. It needs to be in the order of thousands, actually.
Okay.
So I cannot provide the exact size of the data set we use,
Right.
but it needs to be in the order of thousands. Yeah.
Okay. Another question: what is the more success rate the algorithm works? This is kind of broken up, but text-based or image-based for product recommendation. I guess what's the most successful algorithm?
It was actually the hybrid. So it was combined, as I said, the multi-model model that we built for collection, which uses both features from image and from text. And in our paper that we published in Rixis, it is also in the resources slide. We put out the comparison between text only versus image only versus. So the hybrid multi-model technique outperformed both text only and image only. And I remember like the offline validation, like the manual validation where people go and check the recommendation if it is relevant or not manually. That validation of thousands of recommendations showed that the accuracy of that algorithm hit 98% accuracy, which was a huge success actually.
Okay, and we just have two more and we'll end it there. Another one from Ryan, following up to the last Home Depot question. Won't the model's performance be restricted to the quality of your labels then?
Absolutely. All the machine learning, like garbage in, garbage out. This is like a golden rule. So all the machine learning models, supervised learning machine learning models, they all rely on the quality of the labels, of the labeling. So garbage in, garbage out. Yep, that's a bottleneck.
And then last one, can you go over how you regularize again for embeddings? I think it's the same as with other networks, but I just wanted to double check.
Yes, the regularization is, again, like we are on, when it comes to the deep neural network, the regularization or the techniques are the standards in the industry. So it is a dropout or any other technique, it's the same because they are very straightforward deep neural networks. It's not magical. If you think of any architecture here, the plain, they call it even plain deep neural network. So you can take any plain or straightforward or fast forward deep neural network or fully connected deep neural network, and you can put it here in place for the implementation. So the regularization is the same that we use as a standard regularization in the other deep learning techniques.
All right, and that's it. Unless you want to take one more, it's up to you. Last one.
Yeah, let's take last one.
Another one from Ryan. Is your team intending on investigating unsupervised techniques like transformers combined with latent clustering to overcome the labeling bottleneck?
For some use cases, it makes sense. So we are exploring that for some of our use cases, especially for search, not for recommendation. So for search, yes, we are looking to the transformers. We are looking into the unsupervised learning there. But for some cases, like in recommendation, the one I just showed you, it's like for the collection thing, for example, you have to have labeled data. It needs to be supervised because the again, like you have to do lots of let's say there are lots of rules and things that you need to take into consideration when you do when you generate those collection recommendations, and it cannot be pure unsupervised learning. But for other cases, we are looking to transformers. We are exploring unsupervised learning. There is nothing I would say so far like that outperforms supervised learning when we compare both techniques. Usually the supervised learning is outperformed. But so far we are considering that. We are looking to that for some search problems, not recommendation problems.
Awesome. Well, I know I learned a lot today, and a lot of feedback that we got from every session was I know everybody wants to learn more about deploying these models and applications, right? So,
Right.
And then a few people said they hope we can continue this series. So I think the next step is maybe dive deeper, right?
Absolutely. Absolutely. That's a good idea. We will look into that.
Okay. All right. Well, thank you.
Thank you. Thank you, Tom.
All right. Thank you, everybody.